I am Piyush KP, Assistant Professor, Department of Electronics and Communication Engineering, Amrita School of Engineering, Coimbatore. Today we are starting with our first lecture on LPC2148 course. Before going into details of the LPC2148 course, we would like to discuss about the basics of embedded systems. Right, so we'll move on to that. So what do you mean by an embedded system? It is nothing but a system in which you are embedding a firmware. That means a software is embedded into a system. That whole system you will call it as a embedded system. So embedded system is nothing but a hardware plus a software. The embedded system will be having two parts, hardware as well as software. So these are the examples of embedded systems in your day-to-day life. Almost all the places embedded systems play a major role. For example, in the case of avionics, or in the case of communication equipments, or in the case of automobiles. In all these cases, you can see embedded system will be playing a major role. In the consumer electronics, office equipments, household equipments, etc. also you can see those embedded systems. Whatever you are thinking in your day-to-day life, it can be classified as a kind of embedded systems. Whether it is your washing machine or TV or whatever it is coming under the category of embedded system. So nowadays, almost all the category of devices what you are seeing in your day-to-day life is coming in this category known as embedded systems. So if you are writing a formal definition for an embedded system, it is a system in which a software is embedded into a hardware. That is a formal definition you can give. There are several other definitions also, but I would like to use this definition. So what will be the core part of that system? The core part will be a programmable device, and that programmable device can be either microprocessor, microcontroller, or FPGA, or whatever it is. That we will see later. So nowadays, automotive field or automotive domain plays a major role in the case of embedded devices. Nowadays, in most of the car, there are more than one processor. Generally, there will be more than 80 processors in some high-end cars, and it will be of different types of microprocessors and microcontrollers will be there. They will be classified based on the functionality. Say basic microcontrollers will be used for controlling, say, power window, or say lighting system, etc. And more complex systems such as say 32-bit or 16-bit microprocessors will be used for controlling, say, engine. You will be having something known as engine management unit or engine control unit. They will be playing a major role in controlling your automobile. So for such application, you will be using some higher end microprocessors. For the other application, you will be using lower grade microprocessors or microcontrollers. So in a particular car or an automobile, there will be different kinds of embedded systems fixed into that. So let us see what are the basic operations done by an embedded system. So these are the basic three operations. Whatever embedded system you are taking, only three operations will be done. First operation will be sensing, second operation will be processing, last operation will be actuating. Whatever embedded device you are taking, whatever operations they are doing, it can be classified into these three categories. So let us take a typical example of a temperature controller. So if you are drawing a block diagram for a temperature controller, what will be that? It will be something like this. So what does a temperature controller do? It is nothing but it will control the temperature of a room. How will you control the temperature of a room? Before controlling, it needs to detect the present temperature. Then only it can control. So how it will sense or detect the present temperature? That operation is known as sensing operation. For that, you will be using any kind of temperature sensor. Right? Then that temperature value, sensed value, should be processed. Because how it is processed? If the temperature value is above certain threshold, you need to bring down the temperature. If the temperature is below certain threshold, you need to bring up the temperature. So you are maintaining a temperature within a limit. That is known as a temperature controller. So where will be this processing done? It will be done on a processing device. For my example, I have taken microprocessor as a processing device. Why I am taking microprocessor means I need to clarify what is the difference between microprocessor and microcontroller. So for now, time being, I am taking a microprocessor. So whatever sensed value you are sensing from the temperature sensor will be sent to a microprocessor in my case, and the processed output will be sent to a actuator. Actuator, what does it do? Actuator is a device which will perform some actions. So in my case, actuator is nothing but it is going to control a fan or an AC or a heater. So when the temperature is above certain threshold, it will switch on a fan or a AC, and when the temperature is coming below certain threshold, it will switch on a heater. So by controlling the cooler or AC and the heater, you are maintaining a temperature within a certain limit, right? So that controlling the heater or a cooler, that process is known as a actuation or actuating. That will be done by using an actuator. What are the actuators I am using? Heater or an AC or a fan. These are the actuators. So only three operations will be done. Present temperature will be sensed using a temperature sensor. Sensed temperature value will be processed in a microprocessor, and after processing, the final decision will be sent to an actuator such as fan or heater, etc. So these are the three main operations. Then why you are using the intermediate blocks? Say for example, you are using a basic temperature sensor, say LM35. The output of the temperature sensor LM35 will be analog in nature, right? But your microprocessor, what you are using is nothing but a complex digital device. So how will you send an analog signal to a digital device? It is not possible. So somehow you need to convert the analog value into digital data. For that, you are using something known as ADC, analog to digital converter. So whatever sensed temperature value which is in analog format will be converted to digital and will be sent to the microprocessor, which is a digital device, and the processing will be done there. Finally, the microprocessor should control the actuator. Say for example, your ceiling fan. It is operating on say 230 volt AC, and it will, let us take, it will take less than 1 amps current. But your microprocessor cannot supply that much amount of current. Typically, a microprocessor will be able to say supply around in say microamps, say 20 microamps. 8085 can supply only say around 20 microamps current. But your fan requires less than say around 1 amps, right? So how will you control the fan? You cannot directly control. You need to have a kind of circuit known as driver. What does the driver do? With a low current signal or a low current voltage, you are going to control a high current device. That is known as a driver. This driver can be either an amplifier or a switching device such as relay, then contactor, etc. Right? So microprocessor will control the actuator with the help of a driver. So these are the 5 blocks present in a temperature controller embedded systems. So whatever embedded device you are taking, you can draw a block diagram like this. So in my present example, I am using microprocessor as a processing device. So let us take, if I am replacing microprocessor with a microcontroller, what modification I need to make in this block diagram, right? That is what you are going to see in the next slide. So here I am replacing microprocessor with a microcontroller. So what replacement I have done? I was able to remove one block from this, that is a ADC block. Why? Because nowadays most of the microcontrollers are having inbuilt ADC in the controller itself, right? So what is a microcontroller? It can do, it is a processing device. Along with the processor, it is having some additional peripherals such as ADC, timer, etc. So if you are using a microprocessor, you need to attach an external ADC chip. But if you are using a microcontroller, you don't need that external peripheral because it is already present inside the microcontroller. So that is the difference between microcontroller and a microprocessor. So microprocessor is generally used for processing application, but it will be having less peripheral support. Microcontroller is used for controlling application, so it will be having more internal peripherals. So that is what I have written here. So microprocessor, it requires more external hardware support such as ADC, RAM, ROM, etc. But so it is used for only processing kind of application. But microcontroller, it is used for controlling application. So it requires only very little external support, because most of the peripherals such as RAM, ROM, ADC, timer, etc. are present inside the controller itself. Right. So there in the market there are several kinds of microcontrollers available. So why you are going for a embedded systems? These are some of the reasons. You can reduce the number of components. Say for example, if you want to design a temperature controller using a normal, say, digital or analog circuit, it will take a you need to use so many op amps and digital ICs. But here your hardware remains the same. Only a microcontroller, sensor and actuator will be there. Only the software you need to change. So the number of components used in your circuit can be reduced. So when you are reducing the number of components, size also will be reduced. When you are reducing the size, cost also will be reducing to a certain limit. Then power consumption also will be reduced, because each component will be taking a little amount of current. So if you are able to reduce that, power consumption also will be reduced, and easier upgradation and troubleshooting. That means if you are having less number of components, it will be easy for you to troubleshoot and maintain. Otherwise, so much of time you need to spend on that to find out where the fault is. And this embedded devices will be used for specific controlling applications. So this is what I have told. What do you mean by microcontroller? So microcontroller is nothing but it is having a CPU or a processing unit along with other peripherals integrated into a single chip. So that is a microcontroller. So generally microcontroller will be a most important part in a embedded system. So these are some of the various kinds of microcontrollers available. Generally, the microcontrollers are divided or classified based on how many bit data it can handle. So there are 8-bit microcontrollers, 16-bit microcontrollers, 32-bit microcontrollers, etc. So now we will be dealing with LPC2148. It is coming under the category known as 32-bit microcontroller. Then next we will deal with two different categories of architectures available in a embedded system. Whatever embedded devices you are going to design, you will say you will be dealing with these two type of architectures generally. So it is known, one is known as Harvard architecture, other one is known as John von Neumann architecture. So what do you mean by Harvard architecture? In the Harvard architecture, you will be having a CPU and a separate data and a separate program memory will be there in the case of Harvard architecture. So what will be advantage? From the CPU, data can be sent through a bus directly to the data memory. That bus is known as the data bus, and through another bus you can send it to the program memory, that is known as program bus. Right. So in a particular time, you or in a say in the same time you can send the data as well as program to and fro from the CPU. That is advantage. But if you are using John von Neumann architecture, you will be having only one bus. Bus means it is a path through which you are interacting with the memory and the CPU. Right. And if it is written 1 dash and 8, what does it mean? The size of that bus will be 8 bit. That means 8 bit information can be transmitted. So in the case of John von Neumann architecture, only one bus will be there for sending program as well as data. Right. Because whatever embedded system you are programming, you need to write a program, and that program will be used for manipulating some data. Right. Say for example, you are writing a program for addition of two numbers. So those two numbers are the data, and the program will be your program. So both the program and data should be sent to the CPU, or the operations that has to be done on the CPU, both the program and data are required. So if you are going to send the data and program simultaneously to the CPU, you should use Harvard architecture. Otherwise, you should go for John von Neumann architecture. Nowadays, most of the controllers are coming under Harvard architecture. Then another category of process are known as RISC and CISC. RISC means what? Reduced instruction set computer. CISC means complex instruction set computer. So reduced instruction set computer, from the name itself you will get some idea that very less number of instructions will be there, but those instructions are capable of doing more operations in a single cycle, right? So in the reduced instruction set computer, one operation will be generally single cycle operation, right? In the case of complex instruction set computer, each instruction will be taking multiple number of cycles. That is one of the important problem there. So that is the difference between RISC and CISC. Main difference is less number of instructions, in the other side more number of instructions will be there. So here you need to most of the instructions are single cycle instructions. In the complex instruction set, most of the instructions are multi-cycle instructions. So these are the difference between CISC and RISC. So our LPC2148 microcontroller comes under RISC category. In this PPT, I would like to introduce ARM processor to you. In the year 1980, RISC concept was developed by Stanford and Berkeley. What do you mean by RISC? We have already seen. RISC means reduced instruction set computing. That means it is a particular type of architecture where the number of instructions are lesser when compared to its counterpart known as CISC, complex instruction set computer. And ARM was developed during the year 1983 to 85 by a company known as Akron Computer Limited of Cambridge. So at that time, ARM was the expansion of Akron RISC machines. And after around 1990, your actual ARM processor was developed, and then it was given the name Advanced RISC machines. So initially when it was developed, it was known as Akron RISC machines. Then by around 1990, actual ARM processor limited company was formed, and it was given the name Advanced RISC machines. So they have given some advancements over the normal RISC machines and given the name Advanced RISC machines. So how does ARM Limited get the revenue? ARM company does not manufacture any ICs, but what they will do, they are licensing the IP cores of their new microcontrollers or their new microprocessors to the silicon manufacturers who are developing the actual IC. So ARM company is giving the IP. IP means soft core or intellectual property core. That is a soft format of the actual ARM processor. That IP core they will be selling it to the other silicon vendors who are making the IC. So what will the silicon vendors do? They will buy the IP core from ARM company and they will attach their own peripherals, and finally they will manufacture a particular microcontroller with the ARM core. So they will be purchasing the ARM core from the ARM Limited. They will attach their own peripherals to the ARM core and make their own microcontrollers, and they will be giving their own names to it. So ARM is getting revenue by selling the IP cores, and also they will be providing the development tools for configuring this IP core and and for developing programs using this IP core, etc. Then what are the basic features of RISC machines? First feature is that it will be having a large uniform register file. Register file means what? Collection of registers. What do you mean by collection of registers? it is nothing but a memory. So a memory is nothing but collection of registers. What do you mean by register? Register means it is a collection of flip-flops. So the basic unit of memory is flip-flop. When you are taking few flip-flops together, you will get a register. And when you are combining few registers together, you will get a memory or a register file. So the basic RISC machine, the first and important feature is that it will be having a large uniform register file. So it will be having a collection of registers where all the registers will be having same width. That means whatever data you are going to store in each registers, the size of the data will be fixed. So in the case of ARM processor, it is a 32-bit processor. That means it can handle 32-bit of data. So all the registers will be of size 32-bit each, right? Then the next feature is it is having something known as load store architecture, right? Where the data operations will be performed on the register content only. So what do you mean by load store architecture? Say for example, I need to add 1 and 2. So 1 will be stored in a register, 2 will be stored in another register, right? And the operations will be done between the registers, right? Before taking the contents to the registers, where will be the data? The data will be there in the memory. Say for example, I am storing 1 in a particular register. That means it is a part of memory, and 2 it will be there in another register, register 2. So what you will do, you will do a load operation. What you are doing, you will be loading the first operand, that is 1 from memory to register, right? Then similarly you will be loading second number from memory to a register, that is known as load operation, right? From memory you are loading to the register, right? Then you will be performing the operation on the in the ALU. Finally the result will be stored back to the memory, that is known as store operation, right? So like that the load and store operation will be done. So it is known as load store architecture. So you are loading the data from the memory to a set of registers. From the registers you will be operating you will be performing the operation in the ALU. So from the registers the data will be going to ALU where the operation is done, and the result will be stored back to the memory, that is known as store operation. That is known as load store architecture. Then it is having uniform fixed length instructions. That means all the instructions used for writing the program. How will you write a program? You can write the program in two languages. First one is known as assembly language, or in the high level C language. So this one they are talking about the assembly language program. So whatever instructions you are using for assembly language program, all the instructions will be having fixed width or fixed length. What do you mean by that? Here it is a 32-bit processor, so it can handle 32-bit of data, right? In addition to that, instructions what you are writing to this processor will be also of 32-bit. So it can handle 32-bit instructions and 32-bit data in this ARM processor. That is written the next line also, instructions will be of size 32-bit. So instruction as well as data will be of size 32-bit. Then it is having good speed to power consumption ratio. That means the power consumed by the controller will be, or the processor will be very less. Using the very little amount of power, it can do higher operations, more operations. Then high code density. What do you mean by high code density? Means what? In a unit area, how much data you can fill, that is known as a density. So here high code density means in a unit area you can write a code, in a particular area you can write a code, but by writing a single line of code you will be able to do multiple operations. Say for example, there is an instruction known as add EQ, that is one instruction. Add EQ means you will be performing addition of two registers and the result will be stored to another register. This operation will be done only if the zero flag is set. That is meant by EQ. EQ means equal to. See, when the zero flag is set, then only the operation will be done. When will be the zero flag set? Zero flag will be set only when the result of the arithmetic or logical instruction is zero. That means if you are ANDing, or if you are say you are subtracting 5 minus 5, then the result will be 0. Similarly, you are performing a NOT on 1, so NOT of 1 you will be getting 0. So in these operations the result will be 0. At that time zero flag will be set. Zero flag means it is a particular bit in a register showing the status of arithmetic or logical operation. They are present in a register known as status register that we will see later, right? So here add EQ, what does it mean? It will add two numbers only when the zero flag is set. So checking of the zero flag and the addition of the two numbers and storing the result will be done using a single instructions. But if you are doing the same thing in 8085, what you will do? You need to first subtract two numbers, then you need to check whether it is equal. If it is equal, then you need to write another instruction for adding. So 2-3 lines you need to write. But here by using a single line of code you can do multiple operations. That means the single line of code will be acquiring only 32-bit memory area. In the 32-bit instruction you can perform more than one operation. That is meant by high code density. So these are the basic features of RISC architecture. Then next we will see what are the advancements given over the RISC machine in order to make this as advanced RISC machines. So these are the four advancements or enhancements given over the basic RISC machine. First one is it is having control over ALU and shifter for every data processing operations. That means it can control the operations performed on an ALU or a shifter. It is having something known as barrel shifter, right? In the basic ARM architecture itself, it is having a particular block known as barrel shifter. Normally how many times you can shift a number? You can shift a number towards right or towards left only by 1 bit by using right shift or left shift. But if you are since you are having barrel shifter in ALU, what do you mean by barrel shifter is you can perform multiple times left or right shift, right? You can perform around, I think around 32-bit or 40-bit shift you can perform towards right or towards left in a single cycle. You can perform multiple shifts in a single cycle. That is the advantage of barrel shifter. That means you are directly operating on the ALU. Before giving the operand directly to the ALU, you are shifting it in giving, right? So whenever you are shifting a number towards right by 1 unit, you are dividing the number by 2. When you are shifting a number towards left by 1 bit, you are multiplying a number by 2. So those, by shifting the operand, you are actually performing multiplication or division by 2, right? So that operation can be directly done using the barrel shifter. Next feature is auto increment and auto decrement addressing mode. Addressing mode means what? What are the addressing mode means? What are the modes or what are the methods by which you can access a memory, or you can read a data from a memory or write a data to a memory? What are the different methods? So here you are having something known as auto increment and auto decrement addressing mode. Means what? Say for example, I need to add 5 numbers stored in 5 consecutive locations, right? So in C, how will you do that? In indirect addressing mode, how will you do? First you will initialize a pointer to a first location, you will read the data, then you will increment the pointer to the next location, you will read the second data, then you will perform the addition between first and second data, you will get the result. To that result you need to add the third data. How will you access the third data? You need to increment the pointer to the next location. Like that it will be going on. So if you want to do it in C or in assembly, normal C or assembly, what you will do? You need to initialize a pointer. You need to increment or decrement the pointer manually using the program. But here what you are doing is there is a separate, or there is a dedicated incrementer block which can perform this auto incrementing and auto decrementing automatically. The decrementing and incrementing will be done automatically. Once the addition is completed, incrementing will be done automatically. You don't need to manually increment. So if you are using instructions using this auto increment or auto decrementing addressing mode, automatically the incrementing or decrementing will be taken care. You don't need to manually do it. Right? If you are using that instruction, automatically it will increment, and whenever the condition is satisfied, it will stop. That is known as auto increment or auto decrement addressing mode. Next one is known as load store multiple. In the basic RISC machine feature, what I have told, you can do only load store, normal load store. That means single load store only is possible. That means you can load or store only one byte of data or one word of data. But here you can perform multiple load store. That means multiple contents can be loaded from the memory to a register. Similarly, multiple contents of the register, multiple register contents can be stored onto multiple locations in a single cycle, right? So load store multiple instruction, what does it do? It can load as well as store multiple register content or memory content to and fro. In the normal RISC machine, you can only load or store one register content or one memory content, but here you can load and store multiple register contents by using a single instruction known as STM or LDM, store multiple, load multiple. But in the case of RISC machine, you can do only single load store, LDR, STR. Here it is LDM, load multiple, and STM, store multiple. And the last feature is you can have conditional execution for all the instructions. Example I have told, add EQ. That means addition will be performed only when 0 flag is set. So that EQ is the condition flag. Like that you can give 16 conditions. Right? But in the case of normal RISC machine, there are certain instructions dedicated for conditional execution. You can use only that. But here, for all the instructions, you can give condition flag. So these are the advancements over the basic RISC machines in order to make it advanced RISC machine or ARM or ARM. Next we will see the versions of ARM. So these are the versions. First version was developed in 83 to 85. It was having, and these are the special features of each versions. In the first version, 26-bit addressing was only there. That means it can operate only on 26-bit of data or address, and there was no multiply or coprocessor instruction. So each version was having its own significant features. You can go through that. I'll be sharing this PPT. Then version 5, 5T, etc. came. So initially, and how will you how will you refer to ARM naming convention? So say for example ARM 7. ARM 7 is coming under version 3. ARM 6 is coming under also version 3. Then ARM 7 TDMI, it is coming under version 4T. So what do you mean by this T? What do you mean by D? What do you mean by M and I? What do you mean by that? So these are the abbreviations of the suffixes. T stands for thumb. That means it is having thumb instruction support. So ARM 7 TDMI means T stands for thumb, D stands for on chip debugging, M stands for enhanced multiplier, I stands for embedded in circuit emulator. So what do you mean by, so these features are present in ARM 7 TDMI. So it is coming under version 4T. But normal ARM 7 it is coming under version 3. So your LPC2148 microcontroller is coming under ARM 7 TDMI. So what do you mean by T? Thumb instruction support. So in the normal ARM, there are two different types of instruction sets available. They are known as ARM instruction set and thumb instruction set. ARM instruction set, in the ARM instruction set, all the instructions will be of size 32-bit or length 32-bit. In the thumb instruction set, it is a compressed form of ARM. That means all the instructions will be of size, or it can handle only 16 bit of data. In the case of ARM, it can handle 32 bit of data. So if you want to have more processing to be done, you can use ARM instruction set because it can handle 32 bit of data. It can add, say for example, it can add two 32 bit numbers. But if you are using thumb instruction set, you can operate only on 16 bit data, right? So whenever you want to perform, whenever you are going to design an embedded system which is not so complicated, you can use this thumb instruction set. So you can operate only on 32 bit. You can handle only 32 bit of data, right? So that is a basic difference between ARM and the thumb instruction set. So whenever you need to have high performance, you can use ARM instruction set. Whenever you need to have more code density, you can go for thumb instruction set. How are you increasing the code density? Because your instructions will be only of size 16 bit. So instead of accommodating one 32-bit instruction, you can accommodate two 16-bit instructions there if you are using thumb instruction set. So the code density will be increased, but the performance will be degraded because it can operate only on 16 bit of data. Thumb instruction set, ARM instruction set, it can operate on 32 bit data. So whenever you need to have more performance, you will use ARM instruction set. You need to have high code density, you need to go for thumb instruction set. Then next one, it stands for on chip debug, right? General debug means what? If you want to debug a program, how will you do? You need to go line by line. Similarly, if you want to debug a program executing on a microprocessor or a microcontroller, you need to have another external debugger for checking this. Usually it is done like that. But here, this ARM7 TDMI, in the architecture itself, a particular peripheral known as on-chip debugger support is there. So directly you can connect the you can connect your microcontroller to a debugging machine, debugging hardware, right? Otherwise the debugging hardware should be more complicated, but here debugging support is already there. So you need to connect a debugging device to this, so you can debug it. Then it is having enhanced multiplier. Hardware multiplier is present in this processor ARM7 TDMI. M stands for enhanced multiplier. Then I stands for embedded in circuit emulator hardware. So in circuit emulator means emulation means you are mimicking a hardware, that is known as emulation. Simulation means you are mimicking a hardware by using a software component, that is known as simulation. Emulation means you are mimicking a hardware or a microcontroller using another powerful hardware, that is known as emulator. That means whatever you operation it is performed on the actual target hardware, that operation you can see in say real time using in circuit emulator hardware. But here in the architecture itself, already the in circuit emulator hardware is present inside the controller itself, or inside the processor itself. In circuit emulator is there. So directly if you, by using the certain connections known as JTAG, you can perform the in circuit emulation. So like that you can, there are several suffixes available. If E stands for enhanced DSP, etc, etc, can go through this. Then next we will see the basic ARM organization, or this is a architectural block diagram of a basic ARM processor. So it will be having a register file. So register file means it is a collection of registers, right? So if you are taking 8085, you will be having only 6 registers, A, B, C, D, E, H and L. But here in ARM architecture you are having so many registers, around 16 registers are there, and different operating modes are there. All those things we will see later. So register file means it is nothing but collection of registers, and from this in the registers you are storing the data. Let us take, if you want to add 1 and 2, 1 and 2 will be there in two registers, right? First operand will be taken to the ALU, through a bus or a path known as a bus. What do you mean by bus? It is nothing but it is a path through which you can send the data or instruction, right? So bus is a collection of, so if you want to send a single bit of data between two blocks, what you will do? You will be using something known as signal, right? If you want to send multiple data bits between two blocks, you should go for bus. So bus means it is a collection of signals through which you can transfer multiple bits of data or instruction. So the first instruction will be first data will be sent from register file to ALU through the A bus. Second instruction will be sent through the B bus to the ALU. And here you can see that between A and B bus you are having a hardware multiplier. You can perform the multiplication in single cycle. 32 into 32 bit multiplication in a single cycle you can perform. And in the B bus you are having the barrel shifter, what I have told. So you can shift only the second operand which is connected to ALU. First operand will be directly sent to ALU. Second operand will be going through the barrel shifter. So if you want to shift a number, it should be taken as a second operand. Barrel shifter means multiple bits you can shift at a time in a single cycle. And these two data will be taken to ALU. Operation will be performed here in the ALU, whatever arithmetic or logical operation, and the result will be stored back to the register file, right? So this is known as this is a load operation. From the memory you are taking to a register, then this is known as a store operation, right? Then here you can see the incrementer block. Incrementer block is used for auto increment and auto decrement addressing mode, right? Then you can see the program counter. So in ARM, program counter is also a part of register file. One of the register file, it is given additional functionality of program counter, right? So if you want to increment the program counter, you can do the incrementing operation in the ALU. Say for example, if you want an address to be incremented by 10, so you can perform that operation in the ALU, and the resultant address can be written to the register file where the PC program counter is present. So program counter itself is a part of register file. What do you mean by program counter? Program counter is a register which points to the next instruction to be executed. So for example, you have written a program and the ALU, to the ALU you have given the first instruction. So ALU will execute the first instruction. How will the ALU identify or the processor identify that this is a second instruction? How will the ALU get the next instruction? By using the program counter. So once it has given the first instruction to ALU, program counter automatically points to the next instruction. That means program counter will increment by its own, and program counter is nothing but a pointer. It points to the next instruction that is to be executed. Right, so it is a pointer. Initially, let us take program counter is in address location 1000. After reading the instruction from 100, automatically program counter will increment to 10001. Right, you don't need to increment it. In all the process, it is like that. So that is how the processor is keeping track of each line of instruction. So automatically program counter will increment. But here the speciality is that program counter is also part of register file itself. So whatever operation you can perform on register file, all those operation you can perform on the program counter also. That is an advantage. Then in addition to all these blocks, you are having instruction control and decode unit. Then the data in and data out registers. So this is a, so data in register is used for reading the data to the processor. Data out register is used for reading out the data from the processor to the peripherals or wherever it is. So this is a basic ARM organization or basic ARM architecture. Basic ARM architecture. Then all the other ARM versions or the controllers are operating on this, or it will be enhancing this architecture. This is a basic ARM architecture. So by this I am concluding the introduction to ARM. In the next slide, we will try to give an introduction to the LPC2148 microcontroller. Till now, I have given a basic introduction regarding an ARM processor. Next, you are going to see something related with the microcontroller. In this PPT, we are going to deal with the LPC2148 microcontroller. Right, till now we are dealing with ARM microprocessor. Now we are moving on to microcontroller. So what do you mean by microcontroller? It is nothing but microprocessor along with some additional peripherals integrated into a single chip. So this LPC2148 is a microcontroller. It is having ARM7 TDMIS as the ARM core, ARM7 TDMIS as a ARM core inside this, and all the other additional peripherals to this ARM processor, and made a microcontroller and given a name known as LPC2148. LPC shows that it is a microcontroller from NXP. Previously it was known as Philips. So this is a LPC2148 architecture. It is having so many peripherals and ARM7 TDMIS as the core. So this is a most important part of the LPC2148 architecture. So you can see ARM7 TDMIS is the ARM core present in this controller. Then you are having emulation trace module. This is used for in circuit emulation, and this is for test interface. We have seen that it is having on chip debugging support. That means using the debugging interface, you can connect it to a debugging hardware directly. You can connect, no need of any other intermediate device, right? So this is your actual ARM processor, ARM7 TDMIS. This block is your ARM processor, and the other things are the peripherals, right? So how will you connect your ARM processor with the other peripherals such as timer, ADC, etc. by using something known as bus, right? And here in the ARM architecture, in this ARM architecture, there is a special type of bus known as advanced microcontroller bus architecture, or AMBA bus architecture, AMBA, advanced microcontroller bus architecture, right? That is a special type of bus used in ARM products. And this advanced microcontroller bus architecture means, and this AMBA bus architecture, it is having two subdivisions known as advanced high performance bus and VLSI peripheral bus. So you AMBA basic ARM architecture, advanced microcontroller bus architecture is divided into two set of subdivisions known as AHP and VPB. AHP means advanced high performance bus, VLSI peripheral bus. Advanced high performance bus is used for connecting all the advanced peripherals such as your USB DMA, vectored interrupt controller, etc. This is used for handling all the interrupts. What do you mean by this interrupt controller? We will see later when you are dealing with interrupt. And so DMA controller, vectored interrupt controller, let us take these two are the high performance devices. They are connected to advanced high performance bus. And the peripherals such as ADC, external interrupt, timer, etc. These peripherals are connected to VLSI peripheral bus. So why it is connected like that? What is the speciality of AHP and VPB? AHP is a high performance bus. That means it will be operating on higher speed when compared to VLSI peripheral bus. So for example, you will be in your laptop, you will be having a processor, you will be having a hard disk. Processor will be always operating on a high speed. Hard disk will be operating on a low speed. So how will you read a data from hard disk to a processor? Directly you cannot read. Speed mismatching will be there, right? So here, so how will you read it? There is something known as RAM and then cache memory will be there. So a group of data will be taken from the hard disk to the RAM. From that, a group of data will be taken to a cache. From the cache, it is given to the actual processor. That is how the speed mismatch is handled, right? So in our example, let us take your hard disk. Hard disk will be connected to a low speed bus known as, say here, let us take it is connected, it is known as VPP, and your processor will be connected to, say, high performance bus through cache, something similar to that. So the high performance devices will be connected to high speed bus known as advanced high performance bus. All the low speed peripherals will be connected to VLSI peripheral bus. So how will you take a data from a low speed peripheral to the ARM processor? How will you handle the speed synchronization? For that, you are using this block. It is known as AHP to VPP bridge. So what does it do? It will convert the data which is sent from low speed devices which is connected to VPB. That data will be converted to a format that is acceptable by the AHP. Right. So AHP to VPB bridge will convert the data given by or sent to the VPB VLSI peripheral bus to the format that can be taken by AHP. Then from the AHP, how will you send the data to ARM7? Because ARM7 processor, it is operating on the highest speed. AHP is operating on next lower speed. VPB is operating on again lower speed. So how will you send the data from AHP to processor? For that, you are having AHP bridge. So AHP bridge will do the conversion of data from AHP bus format to the ARM7. Right. So this speed mismatch will be handled by AHP bridge. This speed mismatch will be handled by AHP to VPP bridge. That is how the data which is sent from the low speed peripherals will be sent to the data will be sent to the processor which is operating on highest speed. Right. Then in addition to advanced high performance bus and VLSI peripheral bus, there is one more bus known as ARM7 local bus. This is the fastest bus available in ARM. So in ARM, you are having, if you are drawing three subdivisions, you are having ARM7 local bus, AHP bus, VPB bus. Out of this, ARM7 local bus will be operating on the highest speed. Why? You can see that it is directly connected or it is directly interacting with the processor ARM7, right? So ARM7 will be the highest speed bus. Then comes the AHP. AHP will be connected to the high performance devices. So when you are comparing ARM7 local bus and AHP, AHP will be slightly lower speed when compared to ARM7. VPB will be the slowest bus when compared to this. And what are the peripherals connected to ARM7 local bus? RAM, SRAM and flash controllers, and a special peripheral known as fast general purpose IO. There is a normal general purpose IO known as GPIO. This is a fast bus. This will be around 2.5 times faster than the normal GPIO. That is known as fast general purpose IO. It is directly connected to ARM7 local bus, but the normal GPIO will be connected to VPB bus. Right. So in addition to fast GPIO, you are having SRAM controller and flash controller connected to a local bus because they are very important. What is the use of SRAM or what is the use of RAM? RAM is used for handling the data. Right. Right. So if you want to add two numbers, for example, where will you store the data? You can use the RAM for that. Right. So whatever data you need to manipulate, you can store it in the RAM. Say 1 and 2. And say you are performing addition, say add EQ R1 comma R2 comma R3. R1, R2, R3 are the registers used in ARM. It is known as known like that. So add is the instruction, right? And the data will be stored in the registers. So let us take data is stored in the RAM. So RAM is used for storing the data. So here you are having a special type of RAM known as static RAM. That is a normal RAM. So RAM is used for storing the data. Where will you store the program? Here program is add, or where will you store the instruction? That is add. Where will you store that? So the program will be stored in a separate memory known as flash, right? So in this LPC2148, you are having certain KBs of flash, certain KBs of SRAM depending upon the serial number. In 2148, you will be having this much amount of flash and this much amount of RAM, right? So this architecture block diagram is same for 2141, 42, 44, 46 and 48. Only there is a variation in the RAM size and flash size. So what is the use of flash? Flash is used for storing the program, flash memory. So initially, in the olden times, where was the program stored? It was stored in a place known as, or in a device known as ROM, read-only memory. What is the speciality of that? You can only read from that. You cannot write into that. After the invention of the ROM, they have developed something known as PROM, programmable ROM. That means you can write to that ROM only once, then you can read from that, right? So that writing process will be done in the factory itself. That is known as PROM, programmable ROM. Then after few years, EPROM was developed. That means you can erase that and you can rewrite it. How will you erase it? Using something known as ultraviolet rays, right? So there will be a separate EPROM eraser for erasing EPROMs. So how will you apply the ultraviolet rays to the data which is stored in the IC? So for ultraviolet rays, it is a light radiation. It is a light. So how will you take this light to the actual data present inside the chip? So for taking the light, if you see a EPROM IC, in the center there will be a transparent window. Through that transparent window, ultraviolet rays will be taken to the actual silicon chip sitting inside the EPROM. Right? So if you are seeing the old 8085 kit, there will be an IC where the company name will be pasted. Say VI Microsystems. One sticker will be there. So that sticker will be pasted on the EPROM. Why that is pasted? In order to cover the transparent surface. Otherwise, if some sunlight is allowed to fall on that, sunlight also will have certain amount of UV rays in that. So that UV rays may corrupt the data present inside the EPROM. So in order to avoid that corruption, one sticker will be pasted. So that IC is nothing but your EPROM. Then after few years, so here what is the problem? You need to have a separate UV eraser for erasing the program, and it will take around 20 minutes for erasing that EPROM. So in order to overcome, and since UV is a heat radiation, maximum you can perform only 1000 erase cycles. So 1000 erase cycles can only be performed. External additional eraser is required. So and 20 minutes it will take. So in order to overcome all this problem, E square PROM was developed. It is known as electrically erasable programmable ROM. This was developed. So electrically erasable means there is no need of UV eraser for that. Directly using the electrical signals, you can erase the program. So that was developed. So there is a problem with the E square PROM, electrically erasable PROM. What is the problem is that if you want to write some data, you can write only first you need to write in the first register, first location, then you need to write in the second location. Like that only you can write. So bulk read and write was not possible. That is a problem. So in order to have that advantage, they have developed another type of ROM known as flash ROM. That is the latest one. So flash memory, bulk read and write data is possible. That is why in your pen drive you are having flash memory. That is a main advantage, and you can perform the read and write using the normal 5-volt supply, right? And you are having more erase cycles, around 1 lakh times you are having the erase cycles in this flash memory, right? So now you are using the flash memory for storing the program and RAM for storing the data, right? So these are the basic peripherals, and one more peripheral you will see, this is known as a system function peripheral. This is used for handling the clock input given to the controller. So whatever microcontroller or microprocessor you are taking, I told it is a complex digital device, right, which is working on a clock signal, or it is a synchronous digital device. It will be working on a clock. So how will you connect a clock? How will you generate a clock in your digital lab? You will be using something known as trainer kit. Inside that, how will you develop make the clock? Clock means the clock signal, you know, no? How will you develop that clock? By using something known as 555 a stable multi vibrator, right? But the problem with that is that you will not be able to produce accurate clock. Say if you are in the case of your laptop, you are telling that say 3.2 gigahertz. 3.2 gigahertz means always processor should be getting 3.2. If it is varying, if there are some variations in the clock, the working will be affected. So the 555 stable multivibrator problem is that it is not accurate. Why it is not accurate? Because so many passive components are used for generating the clock. Because for making the stable multivibrator, you need to connect some resistors, some capacitors, etc. to the 555. So all these passive components will have their own tolerance. So the clock output will be slightly varied. It will not be accurate. So you cannot use that. So here in a case of microcontroller or microprocessor, how will you generate a clock? You are using a certain peripheral known as crystal oscillator. It is a small component. That component can generate accurate clock, right? So that crystal oscillator will be connected across this Xtal1 and Xtal2. So that is also a passive component. It cannot generate its own clock. So what does it do? From the controller, it will be giving say say for example say pilot clock to the crystal, or it will give a small frequency clock to the crystal, right? So whenever it is getting a small frequency signal, the crystal will start vibrating in its say fundamental frequency, or whatever it is you can call like that, in the desired frequency. So if you are taking 12 megahertz crystal, if the 12 megahertz crystal is getting a low frequency clock from the controller, that crystal will start vibrating in a 12 megahertz frequency. So it will generate 12 megahertz accurate clock in this line. So the crystal oscillator will be having two inputs. One will be clock in, that is shown by this one. So it will be getting the clock in from the controller, and it will start vibrating in its own frequency. That frequency will be connected given back to the controller through this line, right? So this system functions block, it is used for handling the or connecting the crystal oscillator for the clock device. And it will be, and say for example you are using 12 megahertz clock, right? And you are having two PLLs connected to this system functions block. PLL means phase locked loops. If you are not studying now, you will be I think you will be studying in some higher semesters. For the in third or fourth semester, I think you will be studying this PLL. PLL means phase locked loops. It is used for multiplying or dividing the clock. So now you are connecting a 12 megahertz crystal. Let us take your processor should operate on 24 megahertz. What you will do? You need to multiply the clock by 2, right? How will you do that? By using PLL. So this clock multiplication is done by this PLL, right? So whatever crystal frequency you are getting, you can multiply the clock by using PLL 0, and you can connect it to system clock. System clock is connected to all the peripherals and the processor, right? So whatever crystal frequency you are giving through Xtal1 can be multiplied by PLL0, and the output can be connected to processor and the peripherals. That we will see in another lecture how to configure that. PLL1 is dedicated for generating USB clock, 48 kilohertz USB clock. So PLL1 is used for generating USB clock. PLL0 is used for generating system clock. So this is a brief introduction regarding the LPC2148 architecture. Next we will see some basics of the PLL. So this is a PLL. So PLL will be having or PLL is used for multiplying the clock. How the clock is getting multiplied? Internal to the PLL, there will be two sub blocks known as multiplier block and divider blocks. So this is used for the feedback. This is a multiplier. So you will be giving a clock input and you will give a multiplying factor. So if you are giving 12 megahertz, if the multiplication factor is 2, output you will be getting 24 megahertz. So how will the processor verify that you are getting 24 megahertz? This frequency out will be fed back to the input through a divider block. So this is act as a say feedback path. So by configuring the multiplying factor and the division factor, you will be able to configure the actual frequency output. You need to configure the multiplication factor and the division factor in order to configure this, right? So, and there are some limitations also. The input clock frequency of PLL0 and PLL1 should be in the range of 10 megahertz to 25 megahertz. So I told the input clock frequency you are generating using the crystal oscillator, you can connect only maximum of 25 megahertz. From 10 to 25 megahertz crystal only you can connect there, and this can be multiplied to a maximum of 60 megahertz. So if you are giving 12 megahertz, you can multiply it to a maximum of 60 megahertz. So maximum frequency output will be 60 megahertz, maximum frequency input will be 25 megahertz, and for USB clock it will be fixed 48 megahertz, right? And the multiplication of this clock is done by using something known as current controlled oscillator. All these things you will be studying later. So now you identify that the PLL will be having a current controlled oscillator which is performing this, right? So actually for configuring PLL in a programmer perspective, you need to configure only two things. What are they? Multiplication factor and division factor, right? So system functions block is connecting the crystal oscillator is connected to system functions. From that system function block, it is connected to two PLLs. PLL0 is used for generating system clock, that is connected to processor and peripheral. PLL1 is used for generating USB clock. So from the 12 megahertz crystal, you will be able to generate two different kinds of clock, right? Then next step is you need to calculate the multiplication factor and the division factor. How will you calculate that? There are two small equations for that. So here in this equation, say for example you need to generate a 60 megahertz frequency output. You are going to connect a 12 megahertz crystal. So from the 12 megahertz crystal, if you want to get 60 megahertz output, what should be the multiplication factor? What should be the division factor? That is calculated by using these two equations. So CCLK stands for core clock. That is a clock at which your processor ARM core is operating. In my case, my desired core clock is 60 megahertz, right? F oscillator stands for frequency of your crystal oscillator. In my case, frequency of crystal oscillator is 12 megahertz. So when you are connecting 12 megahertz crystal, how will you get 60 megahertz core clock? You need to configure the value of M. What should be the value of M? It should be 5. So M value is nothing but the multiplication factor. It should be 5. Similarly, you need to configure one more factor known as division factor, that is a P. Division factor. This is a multiplication factor. This is a division factor. So if you want to get 60 megahertz clock, what should be the division factor? This is the equation for that. How will you performing the division? By using the current controlled oscillator. So FCCO means it is a frequency of current controlled oscillator. There is a limitation for this also. The frequency of current controlled oscillator should be within 156 to 320 megahertz. It should be within this range, right? So this should be within this range. Core clock is 60 megahertz. So what should be the value of P? You need to calculate the value of P. So by calculating the value of M and by calculating the value of P, you can configure the PLL0. Right? Let us take one example. So this is example. F oscillator is 12 megahertz. CCLK required CCLK is 60 megahertz. So what should be the value of M and P? What should be the value of M from this equation? Same equation. CCLK by F oscillator 60 by 12 megahertz. You will get it as 5. How will you get the value of P division factor? The same equation. What I have only rearranged these two equations. The equation is same. FCCO by 2 into CCLK. What should be FCCO? It should be within this range. So first what you will do? First you will substitute 156 in this equation. So P equal to 156 by 2 into CCLK. Desired clock CCLK is core clock is 60. So you will get it as 1.3. Similarly, you will instead of 156 FCCO, you will substitute FCCO as 320. So 320 by 2 into 60. So you will be getting 2.67. So what does it mean? Your P should be within 2.67 and 1.3. Right? M should be 5. So M I got it as 5. P also should be an integer, and it should be within 2.6 and 1.3. So there is only one integer between 2.6 and 1.3. What is that? It is 2. So if you want to get CCLK as 60 megahertz by connecting 12 megahertz crystal oscillator, the value of M should be 5, value of P should be 2. This is how you are configuring the PLL0. Right? So now you have configured the PLL0 to get 60 megahertz core clock. Then one more clock you need to generate from that. What is that? It is known as a VPB clock or peripheral clock, P clock. Why? Because all the peripherals are connected to VPB bus, VLSI peripheral bus. So you need to calculate the frequency of clock sent to that also. How will you calculate that? So by for that there is a block known as VPB divider block. Right? So the same C clock generated from the PLL0 is given as input to VPB divider. So by configuring the VPB divider, you can configure the VPB clock. Right? So in my case, C clock will be 60 megahertz. By configuring VPB divider, you can configure the VPB clock. How will you configure the VPB divider? So whatever configuration you are going to do in a microcontroller, you need to configure some registers. So register is nothing but collection of flip-flops, right? And generally in a microcontroller, you will be having two kinds of registers. One is known as general purpose registers, another is known as special function registers. General purpose registers are used for storing or manipulating the data. Special function registers are used for configuring the peripherals. So if you want to configure a peripheral, you should use any one or more special function registers. Right? So configuring a register is nothing but register means what? It is collection of flip-flops. How will you configure a register? You need to configure a flip-flop. How will you configure a flip-flop? You by a digital value 0 or a digital value 1. So if you are writing a digital value 0 in a particular flip-flop of a register, it will be doing particular operation. If you are writing 1 in a particular flip-flop in a particular register, it will be performing certain other operation. So for configuring VPB divider, you are having a special function register known as VPB divider register. Right? And I told your ARM or LPC2148 is a 32-bit microcontroller. So LPC2148 is a microcontroller which is having ARM7 TDMIS as a microprocessor inside that. So LPC2148 or ARM, it is a 32-bit microprocessor. So ARM is a 32-bit microprocessor. LPC2148 is a 32-bit microcontroller. What does it mean? It can handle 32-bit of data. That means it can store 32-bit of data, or width of the data bus or the size of the data bus will be 32-bit, or it can handle 32-bit of data simultaneously. Right? That means all the registers, which is registers are, I told you registers are used for storing some kind of data. Since ARM can handle 32 bit of data, all the registers will be of size 32 bit. So here VPB divider is one of the special function register. That register is also of size 32 bit. Right? In that 32 bit, for configuring the VPB divider, you are using only the first two bits, bit number 0 and bit number 1. Right? So if you are writing bit number 1 value as 0, bit number 0 value as 0, that means you are writing 0 0 in these two bit locations of VPB divider. VPB divider is a 32 bit register. That means 32 bits you can write in that register. In that 0th bit location and the first bit location, you are writing a value or data as 0 0. If you are writing it as 0 0, what does it mean? You are configuring the VPB divider in such a way that you will be getting 1/4 of the C clock as P clock. Right. So now your CCLK was, core clock was 60 megahertz. So if you are writing these two bits as 0 0, your P clock will be 1/4 of CCLK. That means 60 megahertz by 4. So 15 megahertz. So by default, bit number 1 and bit number 0 will be written with 0 0. That is mentioned here. Reset value, what do you mean by reset value? When you are resetting the processor or when you are starting the processor, these two bits will be having these two values. That means by default, whatever core clock you are giving, that core clock will be divided by 4 and given as VPB clock or P clock. And by default, CCLK will be 60 megahertz. Right? And how, if I want to configure this VPB divider with say if you want to make P clock as same as CCLK, what should I do? I need to write bit number 1 value as 0, bit number 0 value as 1. So if you are writing 0 1 here in VPB divider register, you are configuring VPB bus clock as same as the processor clock. So if you are writing 0 in this bit, 1 in this bit, what clock you will be getting here? Same 60 megahertz you will be getting. Similarly, if you are writing bit number 1 as 1, bit number 0 as 0, what you are doing? You are configuring the VPB bus clock as 1/2. That means if you are writing in bit number 1 as 1, bit number 0 as 0, 1 0, if you are writing in this register, your peripheral clock will be half of CCLK. So CCLK is 60 megahertz, P clock will be 30 megahertz. So by default, CCLK will be 60 megahertz, PCLK will be 1/4, 15 megahertz. Why it is 1/4? Because the reset value of VPB divider bit number 1 and 0 will be 0 0. If you are writing 1 1, it is don't care. Right? So you can have 3 configurations for the VPB divider. This is very important because peripheral clock is connected to all the peripherals. So whatever calculation you want to perform on any other peripheral, you need to use this clock for the calculation. 15 megahertz. You should not use this. So till that you have seen the basics of ARM processor, ARM LPC2148 microcontroller. Next we are moving on to the first peripheral known as GPIO. GPIO stands for what? GPIO means general purpose input output peripheral. Right. So this is a peripheral, something similar to ADC. So it is a peripheral present in LPC2148 microcontroller, which is used for interfacing general purpose input or output devices. What are the input or output devices? For example, LED. LED is the simplest output peripheral output device you can connect it to this microcontroller. Similarly, can you tell one input device? Say switch. So switch is a basic input device you can connect it to a microcontroller. So if you want to connect input or output devices such as switch, LED, etc., etc., you need to configure general purpose input output peripheral known as GPIO peripheral. So this is the first peripheral you are going to see, right? So GPIO peripheral means it is nothing but, so general purpose input output peripheral is nothing but collection of pins, right? So LPC2148 is a 64 pin IC microcontroller. It is having a package known as LQFP, low profile quad flat package. Quad flat pack. Normally you may have seen DIP package, dual inline package. That means on both sides of the IC pins will be there. That is known as DIP. But your LPC2148 is coming under quad flat package. That means on all four sides pins will be there. And here it is coming, it is having special packaging known as LQFP, low profile quad flat package. Low profile means the thickness of the IC will be very less. That is known as low profile quad flat package. So it is a 64 pin quad flat package. This will be pin number 1. This will be pin number 64. So GPIO means it is a GPIO. We will be generally calling it as GPIO port. Right, so you will be calling the GPIO peripheral as GPIO port. So what do you mean by port? Port in this scenario, port means it is a collection of external pins. So GPIO port means it is collection of external pins. Why you are using? What is the use of these pins? Through these pins you are going to interact with the input or output devices. If you want to connect an LED, you need to connect it to a pin. If you want to connect a switch, again you need to connect it to another pin. So collection of pins, external pins shown in this red color, it is known as the port. Port is nothing but collection of pins, right? And in this LPC2148 you are having two ports. Port is named as port 0, port 1. Port 0 is having 30 pins, port 1 is having 16 pins, right? And I told port 0 and port 1, these are ports. Port is nothing but collection of pins. So how will you refer to each and every pin in a port? Say for example an array, you have taken an array of size 10. How will you refer to each and every element in an array? A of 0, A of 1, etc. Similarly here you are referring like this. P0.0 means 0th pin of port 0. Right? Similarly, P0.1 means first pin of port 0. So P0.25 means 25th pin of port 0. So this is how it is distributed, P0.0 to P0.25. This is how you are referring to each and every pin. Then P0.28 to 31. P0.26 and 27 is not there, you need to keep in mind. Similarly, in port 1, you are having pins from P1.16 to 31. P1.0 to 15 is not there. Why they have decided like that? Based on the chip manufacturer, based on so many criteria, power consumption, the size, based on all this criteria, they have decided on this many number of pins. That is done by the manufacturer. And you can see, so you can see here it is P1.20, P1.17, P1.16, etc. You can see that each pin it is written like this. For example, P1 point, say let us take this P1.16 slash EINT0 slash MAT0 slash CAP0. What do you mean by that? Each pin is given multiple functionality. So actual pin number 46 can be configured as general purpose input pin P0.16 or external input pin, external interrupt pin 0 or match pin 2 or capture pin 2. That means 4 functionalities are multiplexed into a certain pin. Most of the pins are having multiple functionality. Why it is done like that? In order to reduce the number of pins, because if you are giving separate functionality to separate pin, more number of pins has to be there, so size will be more, power consumed will be more, area of cross section of the chip will be more, so many parameters will be there. So in order to reduce the number of pins, they have given multiple functionalities to each pin, right? So This is a pin diagram showing general purpose input output peripheral of ARM7. Now we are going to do the first experiment with LPC2148. The first experiment will be blinking of some LEDs connected to GPIO port. So here I have connected 16 LEDs from P1.16 pin number P1.16, that is 16th pin of port 1 till 31st pin of port 1 P1.31. So 16 pins I have connected from P1.16 to P1.31 through 100 ohm resistance. So you are going to write a program for blinking of these 16 LEDs connected to port 1. So these are the steps for blinking of these LEDs. So first step, what will be the first step? In the previous slide I have told that each pin is having multiple functionality. So in this case I need to configure P1.16 to P1.31. These 16 pins I need to configure the functionality as GPIO port, because these pins can be configured as a ADC or timer or external interrupt, etc. In my experiment I need to configure P1.16 to 31 as GPIO port pin, right? So that is the first step. Second step, I need to configure the direction of these pins P1.16 to 31. So whatever GPIO port you are taking, you need to configure two main things. First one is known as the direction, second one is known as the data. 16 to P1.31. So what should be the direction of those pins? Those pins should be configured as output pins or output port pins. That means the direction of those pins should be output. Why? Because LED is an output device. So if you want to make the LED on, you need to generate a current signal or a voltage signal from the pin to the external world. So if you want to generate a signal in a pin, that pin should be configured as output port pin, or the direction of that pin should be output. So since I am connecting the LED or output device in my experiment, those pins, pin number P1.16 to 31 should be configured as output pin. Similarly, if you are going to connect a switch to that pin should be configured as input pin. Why? Because the switch is an input device. So when you are pressing a switch, you are giving a signal from the external world to the microcontroller. So in that case, that GPIO port pin should be configured as input, right? So you need to configure a pin as input or as output depending upon the device which you are connecting. In my case, I am connecting an LED, so it should be configured as output pin. If you are connecting an switch, it should be configured as input pin. So the first main parameter you need to configure in a GPIO configuration is direction of that port pin, right? Second parameter you need to configure is that you need to configure the data of those pins. So data means what? Say in my case you are connecting an LED, so you are configuring the direction as output. Then I need to make the LED on. How will you make the LED on? In that pin you need to write a logic high signal. So logic high means VCC or the supply voltage of this controller will be generated in that pin. Here LPC, all the ARM based microcontrollers VCC is 3.3 volt. You need to keep it in mind. Most of the other microcontrollers like Arduino, Atmel, etc., they are PIC, etc., they are operating on 5 volt VCC, but ARM based microcontrollers will be operating on 3.3 volt VCC, right? So if you want to make the LED on, you need to generate a VCC of 3.3 volt or in that pin. So if you want to generate a 3.3 volt VCC there, in digital you need to write a logic 1 there or logic high there. Similarly, if you want to make the LED off, you need to write a digital 0 or logic low there in that pin. When you are writing logic low or 0 in that pin, because each pin you can write either 0 or 1 as data. So if you are writing a logic 1 or data as logic high, that pin will be generating VCC. If you are writing a logic low to that pin or logic 0 to that pin will be generating ground or the ground or 0. Right. So if you want to make an LED on, you need to write a logic 1 to that pin. If you want to make that LED off, you need to write logic 0 to that pin. That means you are writing 1 or 0 as data to that pin. In the previous step, you are configuring the direction of that pin. In the next step, if you want to make the LED on, you need to write a logic 0 as data. Right. So you are configuring two parameters. One parameter is known as the direction, another parameter is known as the data. These are the two parameters. And how will you configure the direction and data? We'll see. So these are the main steps used for blinking of an LED. First step is you need to configure the functionality of those pins as GPIO port pin. Second step is you need to configure the direction of those pins as output port pin or output direction, because you are connecting an output. LED is an output device, you are connecting that. Next step is that you need to write a logic 1 as data to that pin, so the pin will be generating VCC and LED will be on. Similarly, if you want to make the LED off, you need to write a logic 0 to that pin, so LED will be off. So these are the four steps. So we will see the first step. You need to configure the functionality of P1.16 to 31 as GPIO. So next, you need to see how to configure the functionality of those pins. So for configuring the functionality of a GPIO pin, you are using a register known as a special function register known as pin select register, pin cell register. Previously we have seen a register known as VPB divider. It was used for configuring the P clock from CCLK, C clock. Similarly, for configuring a GPIO, you are having a set of special function registers or SFRs. First set of register is known as pin cell register. These registers are used for configuring the functionality of each pin, because each pin is having more than one functionality. In my case, I need to configure the functionality of P1.16 to 31 as, that is port 1.16 to 31 as GPIO port, right? Not in any other functionality. So I told there are pin select registers used for configuring the functionality. And here there are, in this controller, there are three pin select registers: pin cell register 0, pin cell 0, pin cell 1, pin cell 2. Pin cell 0 register is used for configuring the functionality of pins from P0.0 to P0.15. Right? Pin cell 0 is used for configuring functionalities of pins from P0.0 to P0.15. Similarly, pin cell 1 is used for configuring functionalities of pin from P0 point, that is port 0, 16 to 31. Pin cell 1 is used for configuring functionalities of P0.16 to P0.31. And the last pin select register, pin cell 2 register, is used for configuring functionalities from P1.16 to P1.31. Right. So pin cell 2 register is used for configuring port 1 16 to 31. Pin cell 1 is used for configuring port 0 16 to 31. In my case, I have connected LEDs to port 1.16 to 31. So I will be using pin cell 2 for my configuration of the functionality of port 1. So this is the pin cell 2 register description. So register description shows what are the functionalities of each pin. When you are configuring a particular bit, not pin, bit. If you are configuring a particular bit of this SFR, what will happen? So here you can see that if you are configuring the second bit of pin cell 2 register with a value 0. That means if you are writing 0 value to second bit of this register, you can configure P1.26 to 36. So this is applicable for the other versions of LPC21 series. So in your 2148 you are having pins from P1 point, you are having pins only up to P1.31. You need to keep in mind. So P1.36 will be available in another 214 series. So in our case you are having only up to P1.31. So in my case you can consider, in our case you can consider it as P1.31 to 26. If you want to configure these pins as GPIO, you need to configure, or you need to write this bit value as 0. Similarly, if you are writing this bit number 2 value as 1, you will be configuring the same pins 16 to 31 as debug port pins. So in my case I need to configure P1.26 to 31 as GPIO. So what value should I write? I should write 0 in bit number 2 of pin cell 2. Similarly, I need to configure bit P1.16 to 25 also as GPIO. So what value should I write? I need to write a value 0 in bit number 3. Right. So if I am writing value 0 in bit number 2 of pin select 2 register and value 0 in bit number 3 of pin select 2 register, you will be configuring P1.16 to P1.31 as GPIO. Right. So what value should I write? I need to write a bit value 0 in bit number 2, value 0 in bit number 3. So total pin select 2 register is a 32-bit register. In that only 2 bits you are configuring, right? So if you are taking hexadecimal equivalent of 32 bits, it will be this bit 0, this bit 0. So hexadecimal equivalent will be 0. So if you are writing pin select 2 equal to 0, that means all bits 0, you will be configuring P1.16 to P1.31 as GPIO pins. Right. So if you are writing a value 0 to pin cell 2 register, you will be configuring P1.16 to P1.31 as GPIO. So here 0 means it is actually 32 zeros. You are configuring only 2 bits. So here 0 means it is hexadecimal 0 or decimal 0. That means actually 32 bits will be there. All the 32 bits you are configuring it as 0. That is meant by the 0 actually. So by writing pin cell 2 equals 0, you are configuring the functionality as GPIO. But the second step, you need to configure the direction of these pins as output. Right? Why? Because you are going to connect LED. LED is an output device. So you need to generate a voltage or a signal from the microcontroller to the LED in order to make it on or off. In that case, that pin should be configured as output. So whenever you are configuring an output device, you need to configure that pin direction as output. So here I am going to configure the direction of P1.16 to 31 as output. So how will I configure that? So for configuring the direction of a GPIO port, you are using a register known as IODIR X register. IODIR X. That X stands for the port number. Right. In my case, I need to configure port 1 16 to 31 pins as output. So I need to take a register known as IODIR1 register. This is O, it is not 0. So IO direction register. So IO direction register is used for configuring the direction of a port. 1 means you are configuring the direction of port 1. Right. Again, as I told before, IO direction register is also a special function register. So that also will be having 32 bits. Right. And each bit of IO direction register is having a 1-to-1 mapping with corresponding pins. So bit 0 of IO direction 1 register is used for configuring P1.0th pin, 0th pin of port 1. Similarly, bit 1 of IO direction 1 register is used for configuring P1.1 pin. Similarly, bit 31 of IO direction 1 register is used for configuring P1.31 pin. So these are the pins which are having one-to-one mapping with the IO direction register, right? So by configuring bit 0 of IO direction register, you can configure the direction of 0th pin of port 1, 0th pin. Similarly, by configuring bit 31 of IO direction 1 register, you can configure the direction of P1.31, that is 31st pin of port 1, right? And here you need to keep something in mind. In LPC2148, you are having only pins from P1.16 to 31. So you need to configure only these bits. The other bits will be don't cares for you, right? P1.16 to 31 only you need to configure. So you need to find out what value should be written to bit 0 to bit 31 or corresponding bit. What value, if you are what is the value that is to be written here in order to configure this pin as output or input in the case of direction. So this is a direction register description. So you can see that if you are writing 0 in a particular bit, that pin, corresponding pin will be configured as input. Similarly, if you are writing a value 1 in a particular bit, that corresponding pin will be configured as output, right? So if you are writing 1 here in bit 0, what does it mean? P1.0 will be configured as output. If you are writing 0 here in bit 1, what does it mean? You are configuring P1.1 as input. In my case, I am using 16 LEDs connected to P1.16 to 31. So all the bits from P1.16 to 31 should be written with what value? 1. So 1, 1, 1, 1, 1. Each bit should be written with 1 value. So when you are writing 1, you are configuring that corresponding pin. If you are writing 1 here, you are configuring P1.16. That corresponding pin, you are configuring it as output. So when I am writing 1, you are configuring this as output. Similarly, all the other bits from 16 to 31 should be configured as output. Why? Because you are connecting 16 LEDs. So direction of port 1 you can configure, all the port pins direction you can configure it separately, and all the other pins bits value can be either 0 or 1. It is don't care. So for time being I am writing all these 32 bits as ones. So what will be the hexadecimal equivalent if you are writing 1 1 1 1? What does it mean? 1 1 1 1 in hexadecimal. What will be the hexadecimal equivalent of 1 1 1 1? It will be F. So similarly, 32 ones, if we are writing the hexadecimal equivalent, it will be 0x FFFF. 1F represents 1111, 4 bits. 0x shows that this representation is hexadecimal representation 0x. 0b, if you are writing 0b some value, it shows that bits are binary bits, right? 0d, if you are writing some value, that value will be represented as decimal bits. So here generally in a microcontroller programming you will be using hexadecimal representation. So 1111 31 ones in hexadecimal, if you are representing it will be 0x FFFF. So if you are writing IO direction 1 equal to 0x FFFF, you are configuring P1.16 to P1.31 pins. Those 16 pins you are configuring the direction as output. Similarly, we will take another example. This is not related with our experiment, it is only another example. So let us take your LPC2148. I am connecting two switches in P1.16 and P1.18. I am connecting LEDs from P1.19 to 31. So how will you configure the direction of this? P1.16 and P1.18, those two bits value in IO direction 1 register should be written with zeros. Why? Because these two pins should be configured with direction as input. Why? Because you are connecting an input device switch here, right? So wherever you are connecting an input device, that should be configured with 0. That means you are configuring it as input. And bit number 19 pins from 19 to 31 you are connecting LEDs. So these are bits from 19 to 31. All these pins, each pin is having 1-to-1 mapping, I have told here. So in this case, P1.19 to 31, that is bit number 19 to 31 of IO direction register should be configured with ones. So these pins you will be configuring as output. These two pins you will be configuring it as input. All the others are don't cares, right? So if you are writing hexadecimal representation, what will be that? 1111 means F is also F, F, F. The 4 F's are there. Here it is 1010. It is A. 1010 hexadecimal representation is A. Then FFF. So if you are writing IO direction 1 equal to 0x F F F A F F F, what does it mean? Except these two pins, that is P1 point except P1.16 and P1.18, all the other pins you are configuring it as output. This is how you are configuring the direction. Then in the third step, what you are going to do, now you have configured the direction. Second step, the next step is you need to configure the data, right? Because now you have configured those pins as output. Next you need to configure that pin as, or you need to make the LED on. That means you need to write a data logic 1 into that pin. If you are writing 1, it will be generating VCC and the LED connected to that pin will be on, right? So you are going to configure the data as logic 1 or logic high. So here the same thing. How will you configure the direction? You are using a register known as IO direction X register. That is used for configure the direction. Here you are using another SFR known as IO set X register. Again X shows the port number. Here I should select IO set 1. Right. So IO set register is used for setting the data as 1. Right. It is same as the other one. Here also 1-to-1 mapping is there. So if you are writing a value 1 in bit 0, what does it mean? P1.0 pin to P1.0 pin, you are writing a logic 1. So it will be generating a VCC in this pin. Right. But in our case, I am connecting LEDs to P1.16 to 31. So if you are writing 1 to all these bits, what will happen? In all these pins, 16 to 31 pins, all these pins will be generating VCC or 3.3 volt. Or in other words, you are setting all these pins as logic 1. Right. So when you are writing 1, you will be setting the corresponding pin as logic 1 or LED will be on. So how will you make all the LEDs on? Bit number 16 to 31, in all these bits you need to write 1. So what will be the hexadecimal equivalent? The remaining bits also I am writing 1. It is a don't care because you are having pins from P1.16 to 31 only in port 1. So what value should I write? IO set 1 equal to 0xFF. So wherever I am writing 1, those pins will be generating VCC. Right. So when I am writing a logic 1 to a bit corresponding pin, it will generate VCC. In my case, all the pins I need to generate VCC. So all the 16 pins will be on. So I am writing IO set to 1 equal to 0x FFFF. So my LED, all the LED will be on. Next step, what should I do? I need to switch off all the LEDs because I am going to write a program for LED blinking. How will you generate LED blinking? You need to make the LED on, then after some time you need to make the LED off. So now I have in the previous step I have made all the LEDs on. In this step I am going to make all the LEDs off. So for making it off, what should I do? Again I need to write a data as logic low. Previously I have written data as logic high, so LED will be on. Here I need to configure the data as logic 0 or logic low, so the LED will be off. So for writing or for setting the pins, you are using an SFR known as special function register known as IO set register. Similarly, for clearing a pin or for writing 0 to a pin, clearing means you are writing logic 0 to a pin. For that you are having another SFR known as IO clear register. Again X shows the port number. So I should take IO clear 1 register, IO clear 1. So similar to your IO set register, wherever you are writing 1, corresponding pin will be cleared. So you need to keep in mind here for writing 0 to a pin or for clearing a pin, also you are writing 1. For setting also you are writing 1. For clearing also you are writing 1. So if you are writing 1 to IO set register, that pin will be set. If you are writing 1 to IO clear register a particular bit, corresponding pin will be cleared. So for clearing also you are writing 1. You need to keep in mind. So for setting also you are writing 1. For clearing also you are writing 1. But the registers are different. If you are writing 1 in set register, that pin will be set. If you are writing 1 in clear register, that will be cleared. Right? So the same value you are writing. So from bit number 16 to 31, you need to write it as 1. Because all these pins you need to make it as clear or 0. So the LED connected will be off. So you are writing IO clear 1 equal to 0x FFFF. That means all the pins, all the LEDs connected to all these pins will be cleared or switched off. Right? So these are the 4 steps required for controlling the GPIO peripheral or LED blinking program. But here there is one more thing you need to keep in mind. So generally LED blinking means what? You need to make the LED on, then after some time only you need to make the LED off. Because in your eyes, if you want to see something, it should stay in my eyes for at least half a second. Right? So in this program what you have done, you are making an LED, you are making the LED on in one statement or in one cycle. In the next cycle you are making the LED off. What will be the time taken for each cycle? How will you calculate that? You have configured it previously. You are configuring a peripheral known as GPIO. GPIO peripheral, I told all the peripherals are connected to VPB bus, and VPB clock I have configured as 15 megahertz. Right, P clock I have configured it as 15 megahertz, that is 1 by 4th of C clock. Right, in one of the steps here you have configured as by default VPB clock will be 1 by 4th of C clock. So my in default CCLK is 60 megahertz. So P clock will be 1 by 4th of 60, that is 15 megahertz. So your GPIO peripheral is operating on 15 megahertz frequency. So 15 megahertz frequency means 1 by 15 megahertz will be the time taken for one cycle to execute. 1 by 15 megahertz will be less than 1, it will be some point something millisecond. Right. So time taken for execution of one instruction cycle is point something millisecond. Right. Because you have configured PCLK as 15 megahertz. So what does it mean? Your LED will be on in point something millisecond. LED will be off in the next point something millisecond. Right. But I told you if you want to see something, that state should stay in my eyes for at least 500 millisecond. But now I am making the LED on in point something millisecond and making it off in point something millisecond. So it is very low. At least LED should be on for 500 millisecond, half a second. Then only I can see that. Right. So I need to make the LED on, wait for half a second. Right. Then only I need to make the LED off. Again I should wait for half a second. So how will you add this wait states in your program? You need to add some delay. So your actual program steps will be like this. First you are configuring the functionality, then you are configuring the direction, then you are switching on the LED. After switching on the LED, you need to add a delay. Right? Then you need to switch off the LED. Again you should add a delay. Why the second delay is required? Otherwise, after switching off, again it will go to switch on, and you will see that only it will be on always. So for LED blinking, what you should do, you need to write all these 6 steps, right? Out of that, the steps 3, 4, 5 and 6 should be inside a infinite loop. These 4 statements should be inside a infinite loop, because this program is for blinking an LED infinitely. That means you need to switch on the LED, give some delay, switch off the LED, again give some delay. So LED is on and off. Again you need to do this process. So these 4 steps should be in an infinite loop. Then only you will be getting the blinking effect. The other 2 steps are known as the configuration steps. Those 2 steps needs to be executed only once. Right. So once you have configured the functionality as GPIO, until you are reconfiguring it, it will be acting as GPIO itself. Similarly, once you have configured the direction as output, until you are reconfiguring it, it will be configured as output itself. So the first and second step, these are the configuration steps. These 2 steps you need to execute only once. Step number 3 to 6 you need to execute it infinitely, because so these are the actual program steps, these are the configuration steps. So this is how. So this delay you can be you can write it using any for loop or any loop statement. So in this program you will be you will be giving only some arbitrary delay. You are not generating actual 500 millisecond delay, some delay you are generating. So you will be making the LED on, you will generate a delay. That means that LED will be on for that much time. Then you are making the LED off, again you are giving the delay. So LED will be off for that much amount of time. So LED will be on, some delay will be given, LED will be off, again some delay will be given, right? So it will ensure that both on and off state is staying in my eyes for at least half a second. Then only I will be able to see the blinking effect. If you are removing these 2 delays, I can see that LED is always on. That on and off state I will not be able to distinguish. That is why you are adding the delay. Right? So next slide, this is known as a register summary. So whatever peripheral you are configuring, there will be something known as register summary. From this you can identify what are the registers involved in configuring this peripheral. Right. So in configuring this peripheral, you need to configure pin select registers. Right. In addition to this, you need to configure IO set and IO clear registers. So register summary is used for showing what are the registers involved in configuration of a peripheral. So in addition to the pin select registers, you need to add IO set and IO clear register also. Here I have not mentioned that also you need to add. Right. So you can see what are the registers and what are the functionalities of each pins. So here I am using pincel 2 register. So that functionality I have specified. If you are configuring pin number 2, bit number 2, you can configure it as GPIO or debug port. If you are configuring bit number 3, you can configure it as GPIO or trace port. Right. So these are the steps involved in blinking of an LED connected in GPIO port P1.16 to 31. Next, you are going to see how to write a program, actually write this program and execute it in a software known as Skill. Now we are going to see how to write the program using Skill Microvision 4. So for opening the Skill Microvision, you can click on this icon. I am using Skill Microvision version 4, right? So this is a Skill IDE. This is IDE used for writing the program. IDE means Integrated Development Environment. So in this environment, all the editor, compiler, assembler, all the tools are integrated into this environment. That is why it is known as IDE, Integrated Development Environment. So the first step of doing this program will be creation of a project. So for that, you can click on this project toolbar. You can click on this, then click on new Microvision project. Click on new Microvision project. Then it will be asking for the location to store the project file. So first what you need to do is you need to create a project folder, because while you are creating a project there will be so many files associated with it. All these files should be kept in a project folder. The first step is to create a project folder. And one more thing you need to keep in mind, this project folder should be created under any one of the drive directly. Don't create it in the desktop or download server, my documents, etc. Because for the desktop the path will be very long. The desktop, the path will be say C colon, say users, username, documents and settings, desktop. So the path for desktop or documents will be very large. Sometimes you will not be able to compile, because maximum path, the number of characters present in a path should be maximum of 64 characters. If it is above that, it won't compile. So you should create a project folder under one drive directly. So I am selecting D drive. Here I am selecting. Then right click on D drive, click on new, right click on D drive, click on new, create a folder. So I am creating it as LPC2148 course folder, LPC2148 course folder. So I am creating that folder, then click on open. So in D colon LPC2148 underscore course, that folder will be open. Inside this, your Microvision project file will be saved. So it will be having UVPROG as the extension. Here you can give the project name. So I am giving the project name as LED blink underscore project. LED blink underscore project. And no need of giving any extension. Automatically the extension will be given as .uvprog Microvision project. Now give save. So when you are giving save, LED blink project file will be saved under D colon LPC2148 course. In the next step, it will be asking for the target. That means for which microcontroller you are going to write the program. So you are going to write the program for LPC2148. It is developed by, it is from a company known as NXP. Previously it was known as Philips. So you can see NXP here. You click on this plus symbol so that NXP will be expanded. NXP will be expanded. Here you need to select LPC2148. 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 So all the descriptions related to the controller will be shown here. It is having ARM7 TDMIS as the core, then 512 KB flash, then 10-bit ADC, UART, I2C, etc. etc. What are the peripherals present in this will be shown here. Then give OK. Then it will be asking for copy LPC2148 startup code to the project file. It is asking for you whether you need to copy the startup code. You need to give yes. Why? Because the startup code contains the basic information required for the processor to work, such as your PLL settings, your interrupt settings. All the basic information will be automatically present in the startup code related with this target. So you need to add that first, otherwise your program won't compile. So you can give S. So you can see that, so this is known as a project explorer on the left hand side. In this, one folder is created, target1. You expand this, so you can see one more folder, source group 1. Expand this also, so you can see that your startup.s file is already created. We will see what are the contents of this. Double click on the startup.s, so you can see the startup.s file is opened here, and when you are scrolling down, you can see all the modes of operation of ARM. All those things we will see later. Then you can see the VPB divider. I have told VPB divider is used for configuring the PCLK. So here VPB divider value is given as 0 0. So 0 0, so the last two bits, 0th bit and first bit of VPB divider was used for configuring the PCLK. So here the last two bits are 0 0. So if you are configuring 0th bit and first bit of VPB divider as 0 0, what does it mean? You are configuring PCLK, that is peripheral clock, as 1/4 of CCLK, and by default in Keel your CCLK will be configured as 60 MHz. So for configuring 60 MHz, M value will be 5, P value will be 2, that we have already seen. So CCLK by default in Keel it will be 60 MHz, and the VPB divider value, the reset value as 0. So your P clock will be 60 MHz by 4. So your P clock will be by default to 15 MHz. Then all the PLL setting. So all the necessary information required for starting the program in this controller, or the basic information required for running the program, will be present in the startup.s file. Right? In ARM.s file means it is a file written in, say, assembly. Right? So assembly file in ARM will be .s. Right? So this is a startup.s file. Then you are going to write the program for LED blinking. So for that, so you can click on either file new, or you can click on this icon, new icon. So a new file will be created here. Here you can type your program. So I have already typed the program, so I am pasting it here. So this is a program. So the first line of the program will be hash include LPC2148.h. That means this header file is dedicated for all the 21 series controllers. So why you are adding this hash include file? Because all the header files are or all the all the SFRs are defined inside this header file. Right? So this is a header file generally used for all the controllers of 21 series. From here it will be redirected to separate header files, and in that header file all the SFRs, special function registers, will be mapped onto its corresponding addresses. So for example in startup.s we will see. So here I am equating VPB divider EQU this address. What does it mean? Because your microcontroller can understand only this address. So this is the actual address of the register. But when you are writing a program, you cannot always keep in mind this address. It is very difficult because so many SFRs will be there. So for the easiness of writing the program, you are giving a name for this address using an assembler directive known as EQU, equate. So assembler directive, what do you mean by assembler directive? Assembler directive gives directions to the assembler. So assembler cannot execute the assembler directive. Assembler will be given directions by giving this assembler directive. So what direction this EQ is giving to the assembler? It is telling the assembler that assembler give a name VPB divider to this address. So that when I am writing a program, instead of writing this address, I can use this name. So this is how you are equating an address to a name. So in the LPC21XX .h and the corresponding header files, what will be written there? All the SFR's address will be equated to its corresponding name. In startup.s itself, we can see so many addresses are equated to its names, addresses and values also. Because here VPP divider value equate means you are equating value as this. So you can use this as the value. Here you are using this as, so here you are using this as address, here you are using it as value. So instead of value, if you want to give a name, or instead of address, if you want to give a name, you can use equate. So all those SFRs will be equated to its corresponding names in the header file. That is why you are adding this header file. If you are not adding this header file, the controller cannot understand what do you mean by pin cell, what do you mean by IO direction, etc. Because these names are equated into its corresponding address in the header file. Right? The first line is that. Then this is a main program in the main. Then what was the first line of my code? You need to configure P1.16 to P1.31 as GPIO port. The functionality you need to configure it as GPIO port. For that you are using pincell2 register. Pincell2 is used for configuring port 1 pin. I have already told pincell0 and pincell1 is used for configuring port 0. Pincell2 is used for configuring port 1. Right? And bit number 2 and 3 will be configuring as GPIO. Then the second step is you need to configure the direction of that P1.16 to 31 as output. How will I do that? For configuring the direction, I am using a register known as IODIR1 register. This is O, it is not 0. So IODIR1 register equal to 0xFFF. That means all bits you are writing it as 1. So whenever you are writing a bit as 1, corresponding pin will be configured as output. So if you are writing 1, corresponding pin will be configured as output. If you are writing 0, corresponding pin will be configured as input. So here I am configuring all the 16 LEDs as output, LED pins as output, P1.16 to P1.31. Then, so I told these two statements should be executed only once because they are the configuration steps. That is why they are given directly inside main. Then after that you are starting an infinite loop using while one. While one means always this condition will be true. So whatever you are giving inside this while one will be executed infinitely. So inside the infinite loop, what you should do? You need to make the LED on. You need to give some delay. You need to make some LED, make the LED off. Give some delay. So how will you make the LED on? You need to configure a data, or you need to write a data 1 to that pin. So how will you configure the data and how will you write a logic 1? So for writing a data as logic 1, you are using a register known as IO set 1. This 1 stands for the port number. Here also this 1 stands for the port number. I am using port 1. So IO set register is used for configuring the data as 1, or if you want to write a data 1 to a pin, you are using IO set 1 register. Right? Then so here all the LEDs will be on. Then you are giving a delay. Why you are giving a delay? I told each state should stay in my eyes for at least 500 milliseconds. So here I am not giving that accurate delay. I am giving an arbitrary delay. So for implementing a delay, I have written a function here. You are passing a parameter here. Inside this, two nested for loop I am using. I am using for a equal to 0, a less than w, a plus plus. W will be passed as a parameter. Right? So here W will be 25,000. So this, and inside that one more loop is there. It is incrementing from 0 to 200. So the actual delay will be 25,000 into 200. So that many times this loop will keep on executing. So the time taken for executing that nested for loop will be the delay that is generated. How much time is taken, that will be the delay. It is an arbitrary delay. So around 25,000 into 200 times it will execute. How much time is taking for executing that much for completing the loop, that is a delay. Then you need to make all the LEDs off. For making all the LEDs off, you are using IO control one, clear one register. This is IO set one, this is IO clear one. So IO clear register is used for writing 0 to that particular pin. Writing 0 means that pin will be generating 0 volt and the LED will be off. Writing 1 means you are generating VCC in that pin and it will be on. Then so after clearing the LED, again you are giving the delay. So these 4 statements will be in an infinite loop, so that your LED will be infinitely blinking. So I have written the program. Next step is you need to save this file as .c file, because you are writing a C program. So you can click on file, you can click on save as. So automatically it will be going to your project folder. Otherwise you need to check whether project folder is opened. D colon LPC2148 underscore course. Here you can give the name of the program. So I am giving it as LED blink.c. .c you should give, because here automatically the extension will not be given, because the compiler, the IDE don't know whether you are writing assembly or C program. Assembly will be having extension .s, C will be having extension .c. So here you should give the extension as .c. So this is a program, we are giving save. So now you have saved the program, right? Then what will be the next step? So once you have saved the program as .c, you can see that color of the program has been changed. The constants will be having this violet color. The whatever commands you are using in C, those will be in bold, etc, etc. So if this color change is occurring, you can identify that you have saved the program with the correct extension. If you are not giving this .c, this will be again in the complete program will be in black color itself, as you have seen before. So once the color has been changed, you can see that program is saved with the proper extension. Next step is you need to compile this program. That means you need to convert the program into machine language code. So for compilation, or for here it is known as build. So for building, you can click on this icon, rebuild or build. Let us take, you are clicking on this. But now when I am clicking on this build icon, you will get an error. We will see what is that error. So click on this. So you are getting an error. What is the error? Target not created, right? And some error it is showing, define not searching arm library, so something it is showing, and it is showing very important error. So this was a warning. What is the error here? It is the no compatible library exists with the definition main. That means the IDE is telling that, at the time of compilation I didn't see any program with a main function. So what does it mean? I have created a program and I have saved the program, but I didn't add this program into the project file, because this is a project explorer. Whatever files that has to be built should be added to the source group. Now it is not added. So now we are going to add this program into the project. So for that you need to right click on group 1. You need to listen here. You need to right click on source group 1, right click on add files to group, source group, click on add files to source group. Then automatically it will go to your project folder, select this file, give add. So you can see that your file is added here, right? Don't give add again, you close this window. So now your file is there, startup.s is there. Now you can give build. So if the program is working fine, you will get an error. You will get, if the program, if there is no error, you will get 0 errors, 2 warnings. So warning was last line in the file ends without a new line. So give build once more. So that file has been gone, right? So now you have compiled the program or build the program, right? So basic build you have performed, but for programming it into the actual microcontroller or before simulation, you need to do some few more steps. So for that you need to click on this target options. You can see a wizard symbol right to the right hand side of target one. that is target options. You need to click on that. Then you will get so many tabs. First tab will be, you can verify it. I have selected the device as 2148. If you want to change the device, you can change it here. Now it is 2148. Next tab is target. Here you are specifying the crystal frequency, extal frequency as 12 megahertz. So by default, you will be using 12 megahertz crystal. Then the next important thing is, what is a ROM and what is a RAM addresses and the size. So here it is showing that your ROM is starting from 0x00 and size of the ROM is this. Similarly, RAM is starting from this address, size of the RAM is this. Right? This is specified by the corresponding microcontroller manufacturers. RAM is used for storing the program. So from which, because in ARM you are having a unified memory, right? Your both RAM and ROM will be having a continuous memory location, right? So it is having a unified memory. So where, from which location your RAM is starting, from which location your ROM is starting, the manufacturer will tell us through the LPC2148 user manual, right? So here the RAM is starting from 40000. It is specified by the manufacturer of LPC2148, and the size is this much. That means from 40000 location, these many locations will be used for RAM. Similarly, from 00, these many locations will be used as ROM. Right? This is provided by the manufacturer itself. Next, you can click on Output tab, right? And if you want to burn this program into a board, or if you want to use this program for simulating a circuit, you need to create a hex file. So for that, by default, this create hex file will be disabled. Now you need to click on, you need to enable this option, then only hex file will be created. So click on this. So previously, when you are compiling, hex file will not be generated, only AXF file will be generated. Once you are selecting this create hex file, in the next compilation hex file also will be created. We will see that. So select this, then no need of going through all the others. Next important option is click on linger tab. Linger, here use memory layout from target dialog. This will be disabled by default. You need to enable this. You need to select this. What does it mean? Use memory layout from the target dialog. What is a target dialog? This is a target. So in the target dialog, I have specified the ROM address and size, RAM address and size. Right? Take this information from here while building the program. That is specified by use memory layout. Use the layout of the memory, that is ROM and RAM. From where you need to take? From the target dialog. Whatever I have specified in the target dialog, take the information from there while building the program. Then only if you are burning into the hardware, it will be working properly. Right? Then only your actual program will be written to starting from this address, data will be written starting from this address. If you are not specifying this, if you are not giving this tick mark, the controller will not be able to know where to write the program and data, so it won't work. So I have configured device, target, output and linger. These are the 4 tabs you need to configure. Give OK. So now I have set up the target options. You need to give build once more. So now only AXF file will be created. When I am clicking once more, you can see that it has created one more file known as hex file. Right? Where it will be created? The hex file will be created inside this D colon. You can go to your project folder. This was your project folder. Inside this, you can see that LED blink project.hex. So the hex file will be generated in the in the name of the project, not in the name of the program. So project file.hex. Some of you will not be able to see this extension. So for that, you need to click on organize. If it is Windows 7, you click on organize, take folder and search options, then click view inside this, by default, this will be selected, hide extensions for non-file types. So you will not be able to see this. You will not be able to see the extension sometimes. So you can click on organize, folder options, view, disable this, hide extensions for non-file types. Disable this, give OK. So you will be able to see all the extensions. So this is the final executable file, right? So .hex file will be the final executable file in the case of embedded system programming generally. So this is how you are compiling or building a program using Keel IDE. In the next session, we will see how to run this executable in a simulator known as Proteus simulator. Next, we will see how to simulate this executable file using Proteus Design Suite 8. So you need to open this Proteus simulator. So this is the icon for that. You can click on that. So Proteus simulator will be opened. Here, first step is you need to create a project. So you can click on this new project. Click on this new project. So project wizard will be coming. Here it will be asking for the name of the project. You can give the name as a LED blink project. Then this will be the path of storing the project, right? Then automatically it is selected as new project. Give next. So here it will be asking for create a schematic. So first you are going to draw a circuit diagram and you are going to simulate. So you by default it is selected create a schematic. By default it is default. Then give next. Here it is asking for whether you want to create a firmware project. That means whether you are going to write a program in Proteus. So you should give no firmware because I have written the program in Keel. So by default it is no firmware. Don't do anything here. Give next. So here it is showing that only schematic is added. Firmware is not there. Give finish. So project workspace will be opened. So this is known as a workspace. In the left hand side you can see the toolbar and this is known as the device list. Whatever device you are going to add in the project will be shown here. Now no devices are there. So as the first step we are going to add few devices. First one will be LPC microcontroller. So in Proteus you are not having 2148. You are having only 2138. There is no problem in that. Only few differences are between 2148 and 38. So instead of using 48 you can very well use 2138. So for taking the components you need to click on this toolbar, this op-amp symbol, that is known as component mode. Whenever you want to add a component you need to click on this component mode, right? You have selected component mode, then you need to click on this P, that is pick from libraries, right? First you need to click on component mode, then click on this P, pick from libraries. Here in the keyword section you need to give LPC2138, LPC2138. So it will be shown here LPC2138, right? Then double click on this. When you are double clicking on the result you can see that in the device list LPC2138 is added, right? Controller you have added. Next device you need to add is a LED. So for taking LED you can give LED hyphen yellow. For time being I am taking yellow LED. So LED hyphen yellow. So you'll get yellow LED active animated LED model, right? So you double click on this also. So that also is added. Then let us take for time being we are only using these two. For the simulation purpose you don't need that resistance. So for time being you are adding these two only. Then you need to close this window. This is a pick devices window. You click on OK. So now two devices are added here. Next what you are going to do, you are going to draw the circuit diagram. So first you are going to draw the circuit diagram. So first you are going to add the controller. So first click on this controller. Then you need to take it to this workspace. This is workspace. So no need of dragging the controller. You simply click on the controller. Don't drag. Move the cursor to the workspace. No need of dragging. Move the cursor to workspace. Click once. When you are clicking once, you will be getting a skeleton so that you can keep it wherever you need. When you are clicking once, you will be getting a skeleton. Click once more. So your controller will be fixed here. Controller is fixed. Now you are not able to read the whatever pins it is written here, so you can zoom it by clicking on the zoom in icon. So let us take, you are clicking 2 times. So when you are clicking, when you are zooming more, you can see that some of the portion has gone outside the viewable area. This is a viewable area. So how will you make it visible? For that, on the left hand side you can see one green box here on the left hand side. Click on that once. So when you are clicking on that once, that mouse has been changed to this plus symbol. So wherever you are keeping that green area, that green area means your visible area. You keep it wherever you need. So for time being, I am keeping it here. So once you are keeping the green box wherever you need, click once more. So when you are clicking, you can see that plus symbol has been changed to the arrow and viewable area is fixed now. Right. So now the first step for writing the program is that you are going to connect the VCC to the controller, VCC and ground. Right. So these are the VCC pins. These are the ground pins. All the VCC and all the ground pins should be connected to where here in ARM controllers your VCC is 3.3 volt. Right. You need to give 3.3 volt. Don't give 5 volt. So for that, for taking the supply, you need to click on this generator mode. In the toolbar, you need to click on this icon generator mode. So you will get all the generators, all the waveform generators you will get. From that, you need to click on DC generator. Click on DC generator. Again, no need of dragging. Click here once. So you'll get the generator. Then what you need to do? You need to make the connection. How will you make the connection? You can click on the starting point. So when you are clicking on the starting point, you will be getting a red square. Click there once. Click there once. Again, don't drag. Then move your cursor to the ending point. Again, you will get a red square. Click there once more. So these two are connected. Similarly, you connect all these things to this VCC itself. So you are connecting like this. I have made all the connection. So I have taken a DC source. I have made the connection to all the VCC pins. Then you need to configure this VCC as 3.3. How will you do that? You need to double click on this DC generator. Double click on this. Then you will get here. You can configure here what voltage you need to give. You give it as 3.3. You can give it as 3.3 volt. You are specifying the voltage as 3.3. Give OK. So now I have configured the DC source. So generate 3.3 volt. Then all these pins should be connected to ground. So for taking ground, you can click on this terminals mode. Can you see this? Terminals mode. Click on this. All the terminals you will get. From that you click on ground. Click on ground. Don't drag and keep it here. Similarly, I have told in the previous time, you connect all these pins to this ground. No need of dragging. Click at the starting point. Click on the ending point. So I have made all the connections to ground, all the connections to VCC. So VCC I have configured, I have connected. Next step is I need to make the connection with the LED. So how will you take that LED? Now you are in terminals mode. You need to go back to components mode. So again click on component mode. Click on component mode, then only you can see that. And LED should be connected to port 1 pins. Which are the port 1 pins? P1.16 to P1.31. You can see here. For time being, I am connecting only one LED. So in one pin, so click on LED yellow. Click here, right? Then one end of the LED you need to connect it to, say you are connecting to P1.16, make the connection. The other end you need to connect it to ground. How will you take the ground? You need to again click on terminals mode, take ground, keep it here, make the connection. Similarly, I can connect one LED here also, or here also I can connect one more LED. Click on component mode, take the LED, make the connection here. Then I am connecting it straight itself. This also you can connect it to the ground. So one LED I have connected to P1.16, another I have connected to P1.22. In my program, I can connect LEDs from P1.16 to 31. All the 16 LEDs will be working. So I have connected like this. Then, so I have my circuit is ready. My VCC and ground is ready. Next step is you need to configure the clock frequency for this controller. So for that, double click on this controller. Double click on this controller. Here you need to specify the crystal frequency as 12. Crystal frequency you need to specify it as 12 megahertz. You can see it as clock frequency is 12 megahertz. Then in the next step you need to program the hex file what you have created. So that should be shown in the program file. What hex file you need to run here. So click on this browse button, go to your folder. I have created it in D drive, LPC2148 underscore course. Inside this LED blink project.hex file. This hex file should be loaded there as program file. Give open. So LPC2148 course LED project LED blink project.hex. So this is an executable file. This is a clock frequency. Don't do anything else. Give OK. Right. So now I have configured the program. I have configured the clock frequency, crystal frequency. I have configured the VCC. I have connected the LED. Then the next step is you need to start the simulation. For that, on the left hand side bottom you can see an icon that is known as run the simulation. Click on that. So when you are clicking, you can see that your LED will be blinking. LED starts blinking in whatever rate you have configured. If you want to keep an resistance here, you can keep a resistance 100 ohm resistance here also. So the brightness of the LED will be slightly reduced. Right. So if you want to keep the resistance here, you can keep that, no problem. For time being, I am not keeping it here. Right. This is how you are simulating a small LED blinking program using LPC 2148. Here 2148 is not there, only 2138 is there, using Proteus simulator. Thank you all for watching the first part on LPC2148 course. In the next part, we will be discussing about the LED and switch interface using LPC2148 microcontroller and with the softwares Keel and Proteus. Thank you all. We will meet once again.